Our third and final way of solving a system of equations, notice the same system of equations we did in the last two videos. The solution we found was 1, 3 in both cases. The last way to algebraically do this is called the elimination method. So I already have the steps set up, and if you recall from the last video, 3, 4, and 5, as I said, these are the same steps that we're going to take in both situations. It's just how we start the problem. If you remember from substitution, our job was to take one of the equations and solve for a variable. So we solved for y and substituted it in. Sometimes that process can be lengthy. It can create fractions that you have to deal with. This elimination method I like a little bit better because it works in a broader range of situations, and you don't tend to end up with fractions or decimals that you have to deal with along the way. You can kind of avoid it. So the first step is here is the pivotal point. So the goal, before I explain that first step, the goal here is instead of solving for a variable, we're going to try to add these two equations together. So if you did that right now, if we said, okay, let's just add these two equations together right now, we would get a new equation, but it wouldn't really mean that much to us. We can certainly add these. 2x plus negative 4x would be negative 2x. 1y plus 1y would be 2y. And 5 plus negative 1 would be 4. Great, that's a new equation. Does it help me get any closer to knowing what x and y are? Not particularly. So we don't want to just start off by adding the two equations together. We want to add them together a little more strategically, because our goal is to eliminate one of the variables. So usually when you start these, just adding them up straight up will not eliminate a variable. But it's possible that if this was a 4x and this was a negative 4x, you could just add the two up and the two equations together, and you'd be ready to go and keep going and solve for 3, 4, and 5. So there are situations where you don't need to do any special preliminary work. That's why I say over here, if necessary. In this case, it is necessary. So if necessary, we're going to want to manipulate one or both of the equations, depending on everything we need to do. And to manipulate them, we're going to multiply the whole equation by a constant, a number of our choosing. And the goal here is to create one of the variables, whether it be x or y, that has the same coefficient but opposite signs. So when we add them together, they'll cancel out. So that's going to be the key point to starting this problem. If we don't have a variable that has the same coefficient and opposite signs, we're going to have to make that happen. So what we're essentially doing is looking at the coefficients of x or of y. I'll do both. If we're looking at the coefficients of x, we're going to say, well, what's the least common multiple? So that phrase should be familiar. Now we're trying to find a common multiple of 2 and 4. Because we can build these coefficients up. We can never tear them down, so we're going to be multiplying by a number to build them up. So the least common multiple of 2 and 4 should be 4. So this coefficient here, this negative 4x, this is a happy coefficient. It's exactly where I want it to be. But I can change this coefficient. I can make it a 4, and I would want it to be a positive 4, so it has opposite signs. So I'm going to try to make this coefficient a positive 4. I don't really care about what happens to the rest of the equation. I just want to make sure that these two coefficients are going to cancel each other out. So the coefficient we would have to multiply the whole top equation by. This isn't the greatest notation, but it does illustrate that we want to make sure every single piece gets multiplied by 2. Now we can see 2 times 2 will be 4, and kind of distribute this even to the other side of the equation. And I'm just going to rewrite the top equation and the bottom equation right below. So we have 4x plus y equals, oops, I did not distribute. See? Common mistake. 2 times 2 would be 4x. 2 times y would be 2y. And 2 times 5 would be 10. Make sure all of the pieces get multiplied by 2. Otherwise, this is not going to work out so nicely. All right, now we've created or manipulated one of the equations so they have the same coefficient, opposite signs. Now let's take a look what happens when we add these up. Right, our x's, right, will cancel out. Right, and that's going to be step 2, add the equations together. 2y plus 1y, 3y. 10 plus negative 1 will be 9. Then we can solve the equation. Divide by 3. And y equals 3. Right, notice in this case we solved for y first, but that doesn't matter. It's still appropriate. That's exactly what we wanted it to be. From what we saw before, we knew it to be. And the same 2 final steps we take into account as well. Right, we go back to either one of our original equations. Honestly, it could be the equation we manipulated too. Any one of the equations along the way, and we plug 3 into it. So I'm just going to go back up to the top one that we started with. 2x plus y equals 5. Right, we're going to take this value of 3, right, substitute it in for y. And then we would have to solve that. So we can add a negative 3. This marker's not working. There we go. Add a negative 3 to both sides. Divide by 2. And we get an x value of 1. Right, so again, 1, 3, you should always write your solutions as an ordered pair, and I'm sure Math Lab reminds you of that as well, but we're solving for each variable independently and then collecting our answer here as an ordered pair. So 1, 3 works out. So let's revisit the problem from the beginning. This was no problem. We canceled out the x's, right, by getting the same coefficient. I did say that you could do it for either variable. So let's go back and revisit the problem. But now let's cancel out the y's, or eliminate the y's first. Let's see what we would have to do. Right, you'll never have to do it both ways, but just to show you that it doesn't matter. And if I'm looking at the y's, this one might even be easier to do than the last one because they already have the same coefficient of 1. All right, that's great. We want the variable to have the same coefficient, but we do want it to have opposite signs. So it's not quite ideal yet. They do both have a coefficient of 1. All right, but I would like one of them to have a coefficient of negative 1. So it doesn't matter which one I apply it to. So I'm going to do it to the bottom one since last time we manipulated the top equation. Alright, so if I want this coefficient to be a negative instead of positive, well, we can multiply this whole equation by negative 1. Right, I'm going to multiply negative 1, negative 1, negative 1. And we can rewrite the 2 equations, 2x plus y equals 5. Negative times negative will be positive 4x. Negative times positive would be negative y. And negative negative would be positive 1. Right, now we can add these 2 equations together, and we've made it so the y's will cancel out. And now we have 6x is equal to 6. Divide by 6, divide by 6, and x equals 1. So it doesn't matter which variable you choose to eliminate first, we should still get the correct value for that variable that's remaining. Play the same game, go back up to either original equation. We can say 2x plus y equals 5. Take my x value now, substitute it in for x. 2 plus y equals 5. Add a negative 2 to both sides. We get the corresponding y value. Alright, so in this situation, in this problem that I gave you, you only were required to multiply one equation by a constant of your choosing. Right, it's possible, there are scenarios where you would have to multiply both equations. That's why I say over here multiply one or both equations by a constant. In the next video, I'll give you an example of that.